A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about stress transform and principal stresses. So let us get started. The topics for today's lecture are as follows. We will be talking about stress transformation first using the tensor transformation laws that we have learned. Then we will talk about principal stress values and principal stress directions. And finally, we will close the lecture with a discussion on principal planes and principal coordinate axes which are formed using the principal planes. So let's begin the lecture. So we have talked about the fact that the Cauchy stress tensor sigma represents a state of stress in a given coordinate system at a given point P. So let's write it down. So the rows of sigma are simply the traction vectors on three coordinate planes, that is on E1 hat, E2 hat and E3 hat as the cutting planes. And the state of stress, that is sigma, is defined at a given point P. To represent these stress components, we need a coordinate system of choice. So that coordinate system has to be provided so that we know what is the meaning of the different components of the stress tensor sigma. So the coordinate system typically is written as P x1, x2, x3. That is a right-handed coordinate system with the origin at P and the directions as x1, x2 and x3. Now if I transform my coordinate system, that is, I give it an orthogonal transformation like a rotation to get a new coordinate system which is given as P x1 prime, x2 prime and x3 prime, then sigma will transform into a sigma prime in the sense that the 9 components of sigma will change to new 9 components of sigma prime, and that is called a stress transformation. And to do that, I need the information of the transformation matrix A. That is, I need the information about the rotations, the 9 angles of rotations between the base coordinate system and the primed coordinate system. We must note that the physical quantity sigma, in this case the Cauchy stress tensor, does not change as a result of us looking at it in a different way. The physical quantity stays the same as such. It is just its mathematical representation will change because we are looking at it in a different orientation. So it is required to get the 9 components of sigma prime, and for that we use the mathematical stress transformation property. So I'll write that down again, although we've discussed that in the background mathematics lectures. Sigma prime ij is given as AIP AJQ times sigma PQ. So this is the tensor transformation property. We can also call this the stress transformation property. In the symbolic notation, this can be written as sigma prime is A sigma A transpose, where A is the transformation matrix. So these things we have discussed in week 4. But we are discussing that again with the perspective of the stress tensor now. Earlier, sigma was just a second order real symmetric tensor, but now sigma is the Cauchy stress tensor. So we'll try to understand the same ideas from the perspective of now a physical Cauchy stress tensor. Now we move on to the discussion on principal stresses and directions. So let's look at an experiment. So we have an object with a cutting plane. So this is a cutting plane. And this is our part 1 of the body, and we also have a part 2. which is not shown because we're only drawing the free body diagram of part 1, which is created by hypothetically slicing the body through this cutting plane, passing through the point P, and this is the normal vector n hat, which denotes the cutting plane. And we'll see that the traction vector in this case will be in some direction like this, and this is denoted as the traction vector on the cutting plane n hat. So here's the experiment. We change the cutting plane passing through the point P, that is, we try out various n hat values until we find a traction or a traction vector, so that the traction vector points in the direction of n hat. That is, the traction vector is purely normal. There is no shear component on the cutting plane. So when that happens, the figure looks like this, where the normal and the traction vector both are pointing in the same direction. So in this situation, where we have the traction vector pointing in the n hat direction, we can write it as some scalar component lambda times n hat. In the initial notation, it will look like this, where our lambda or lambdas will be called principal stress values, and the ni's or the n hats, the corresponding vectors to the cutting planes on which the traction is normal, is called these are called principal directions. So earlier we had called the lambdas as principal values. Now we call them as principal stress values because sigma is the Cauchy stress tensor. So lambdas are principal stress values. And the plane which is perpendicular to n hat, that is the cutting plane or the cutting planes, are called principal stress planes. So as we said that there is purely a normal stress on these principal stress planes, and there is no shear stress, that is, there is no component of the traction vector along the plane in these principal stress planes, as we can see from this figure. So now once we establish the idea of principal stress planes and principal stress directions, the next job is to find those, and for that we set up the eigenvalue problem like earlier. So using the Cauchy stress formula, we write the traction vector as sigma ij nj. Remember, it was sigma ji nj, but I'm using the symmetry property of sigma, so I can write it as sigma ij nj minus lambda times delta ij times nj equals a 0. This is a null space problem, and we know that solution to this system exists only when the determinant of this matrix is a 0. That is, this matrix is a singular matrix. So we're talking about situations where n hats are non-zeros, that is a non-trivial solution. When we expand this, we get the characteristic equation in lambda, where the coefficients, that is 1 sigma, 2 sigma and 3 sigma, are invariants. In fact, they are called the first, the second and the third invariants of the stress tensor sigma. The first invariant is sigma ii, The second invariant is half of sigma ii times sigma jj minus sigma ij times sigma ji. And the third invariant is simply the determinant of the stress tensor sigma. Now from this characteristic equation, we see that the coefficients are all invariants. So what that will mean is that irrespective of the choice of the coordinate system that I use to represent sigma, that is, I can do any transformation to my coordinate system and I get a different sigma prime, but when I calculate the coefficients, they come out to be exactly the same because by definition these are invariants. So this will mean is that the principal stress values, that is lambda 1, lambda 2 and lambda 3, are all the same irrespective of the choice of my coordinate system. Let's write it down. So the coefficients are invariants in the characteristic equation. So the principal stress values, that is the lambdas, are independent of the choice of the coordinate system. So this basically means that the lambdas and the corresponding n hats, that is the principal stress values and principal stress directions, are properties of the physical quantity sigma. So they are a property of the Cauchy stress tensor, the physical quantity. They do not depend on how we choose to look at the coordinate system. If I rotate my coordinate system, nothing's changing with the physics of the problem. So the principal stress values and principal stress directions will not change. So when we solve this equation, the characteristic equation, three cases are possible. The first case is that we get three distinct lambdas. That is, we get three distinct principal stress values. Now, since the stress tensor sigma is real valued and symmetric, so the lambdas we get as a solution to the characteristic equation will always be real valued. But in case 1, all three are distinct. So the three values will be written as lambda 1, lambda 2 and lambda 3. And typically we write them in the order such that lambda 1 is greater than equal to lambda 2, greater than equal to lambda 3. And corresponding to these principal stress values, we have the directions N1, N2 and N3. And these N1, N2 and N3 are mutually perpendicular to each other. So they form a right-handed coordinate system. And we've already shown as a part of a tutorial problem in week 4 that these n hats are mutually perpendicular to each other. Then we can have a situation or a case 2 where two lambdas are repeated and the third lambda is distinct. So in this case, we get an n3 hat which is distinct, but corresponding to lambda 1 and lambda 2, we get a whole plane with all vectors in that plane being principal directions. In fact, that plane is the plane that is perpendicular to n3 hat. So we write that down here. All vectors in the plane perpendicular 2 n3 hat are principal directions. So that will mean is that if I take sigma ij times nj for an n which falls on the perpendicular plane to n3 hat, we get lambda 1 times n perpendicular j. So I'll write that the vector n perpendicular dotted with n3 hat is a 0. And finally, in case 3, we have all principal stress values repeated. So lambda 1 equals lambda 2 equals lambda 3. And in this case, all directions in our right-handed Cartesian coordinate system are principal directions. That is, if I write sigma ij nj for any vector n, this comes out to be lambda 1 times nj. Now we move on to the final topic, that is on principal planes. We found out n hats, which are principal directions of the stress tensor sigma. So the planes corresponding to these principal directions, that is the cutting planes, which are perpendicular to the principal directions, are called principal planes. Now please make note that principal directions are basically directions which are perpendicular to the cutting plane. So that's the reason we write perpendicular here. Now since we have 3 n hats, which basically form a right-handed coordinate system, as we just mentioned above, so we can form a coordinate axis using these 3 n hats. So these are the principal directions of the stress tensor sigma defined at a given point P. Then we can form a coordinate system. So I'll call this x1 star, x2 star and x3 star. So P x1 star, x2 star and x3 star is called principal coordinate axes, which are formed from the principal directions n hats. So as we said that the physical quantity sigma is not affected with the choice of the coordinate system, in the sense that physically it stays the same, except that the mathematical representation of sigma will change. So nothing stops us from choosing to work in the green coordinate system, that is the starred coordinate system or the principal coordinate axes. So if I transform my sigma from the base coordinate system, that is P x1, x2, x3, to the starred coordinate system, that is Px1 star, x2 star, x3 star, using the transformation matrix A, which basically is a function of the n hats, and we have shown that earlier. It basically contains the 3 vectors n hats as its elements. So when we do this transformation, we get sigma star, which has this form. So sigma star is a diagonal matrix with the 3 diagonal components as lambda 1, lambda 2 and lambda 3. And if I look at the first row, you may recall that this is nothing but the traction vector on the even hat direction, except that in this case we are working in P x1 star, x2 star and x3 star coordinate system. So even hat here denotes the n1 hat direction. One must be careful because now we have moved to the starred coordinate system for representation. So the traction vector on the n1 hat direction, to be specific, is simply having an even hat component. So if I was to draw this, so this is in the starred coordinate system, this is the E1 hat direction, which is the same as N1 hat direction, and the traction vector in this case is also along E1 hat. So that basically means is that these components are zeros. And what do these components represent? Let's look at that. So in this case, we have only sigma star 1 1 as a non-zero value, and sigma star 1 2 and sigma star 1 3 as zeros. So on this cutting plane, that is n1 hat cutting plane, which is in the starred coordinate system, we do not have any shear stress. We have a purely normal stress situation because it's only sigma 1 1 star which is non-zero. And due to its mathematical nature, being a diagonal matrix, it is much easier to work in this starred coordinate system, mathematically speaking, than in any other coordinate system. So this coordinate system is special, and that is the reason it's called a principal coordinate system. So in many cases, we tend to transform our sigma to the starred coordinate system, do all the interesting mathematics in the starred coordinate system, and if required, we transform back to the base coordinate system. So this brings us to the end of this lecture. Today we learned about stress transformations. We talked about principal stress values and principal stress directions. And finally, we talked about principal coordinate axes and principal planes corresponding to the stress tensor sigma. So before we close this lecture, let us have a look at a concept check problem. So the concept check problem for today asks us that why are the principal stress values independent of our choice of the coordinate system at point P. So thank you very much, and I will see you in the next lecture.